Okay, so today I want to look a little bit better into what happens in the rasterization or in the actual rendering onto the screen. A little bit more in the Fragment Shader. The main thing we're going to be looking at is called blending. So it's the idea of basically taking the color that we're putting in and rather than just overriding with it, to somehow mix it with other stuff that ends up in the same pixel. And we're going to look at how OpenGL does this, what policies it has for blending, how we can change and affect these policies, and what values we need to set in the Fragment Shader in order for kind of the blending to have the effect that we're hoping for. So, like so many times before, I'm going to do an image of our pipeline, except now I'm going to, doesn't really matter if this is actually on here now. Vertex Shader, know a lot about what that does. We have clipping, we have window to viewport mapping, but I'm gonna basically take most of this area to look at rasterization. And inside of that, the Fragment Shader. So rasterization, we've gone through that. I kind of want to write up kind of pseudocode for the structure of the rasterization algorithm once more here, and then kind of find out what we can kind of add into that or what we can fit in here. So still going to give myself a little bit more space for that. Just hoping I'd have a strong black marker here. Well, this is going to have to do. Okay, so our rasterization algorithm, we have rasterization here. And we're imagining that this rasterization takes in some points P1, P2, and P3, which are basically points in a triangle that we're rendering onto the screen. At this point, each one of these has X and Y coordinates, which are the screen coordinates that they're going to end up, basically the pixel that they're going to end up in. But they also have other data there, basically values for the varying variables, colors, vectors, things that we need to send between the Vertex Shader and the Fragment Shader. Also pseudo depth values, things like that. So the rasterization was basically, well, start by saying find Y bottom and Y top. So that's kind of the first step, deciding what's the lowest, what's the highest. So we can now go from Y equals Y bottom ranging up to Y top, including Y top. We have some value of Y. So each scan line here. For each scan line, we like to find X right or X left and X right. But inside these scan lines, we also need to find kind of right and left values for all our varying variables. Find B underscore whatever left, B underscore whatever right. So for every varying variable in this, we need to find the left and the right value. Now that we've found these, we can now go along this scan line. So every Y decides in which scan line we are. When we're walking the X, we're basically scanning the scan line. So for X, going from X left to X right. Who remembers what it is that we need to do now that we have these values at this point? Okay, find the value for the varying variable depending on the x. Okay, so now we find the actual v underscore x for every varying variable. So we find the actual value. We're using linear interpolations for all of this. We've gone through that. Don't need to repeat that here. So we find the value. What do we do with this value now?
We add it to the values in terms of color or...
Well, if we're thinking about the varying variables, then what we do basically at this point is we set their values to the corresponding variables in the fragment shader, right? Okay, so we find these basically and set, or in fact, we could wait a moment for this and say, what we also need to do, so we can kind of leave space for that here, we find basically the pseudo depth. Basically for this pixel, or for the fragment, let's say. At this point, we're kind of working within this fragment. So we find the pseudo depth for this fragment. At that point, we can say if, we call it z here, if this z is less than whatever is in the depth buffer at xy, then we continue, otherwise we don't. That's kind of the idea. We could also go in here and say, okay, if we're actually using depth testing, if we're not using depth testing, then we always do what's here. If we are using depth testing, then only if, so we can say, if this is less, just put it on the other side here. So if using, or let's say if GL depth test is enabled, or
should it be and?
Let's check out if it should be and or if it should be or. We'll put the or here and we're going to kind of look at the idea here. Or, what do you say, the z buffer at xy is greater than our pseudo depth. Okay, how does this work? I'm basically saying if GL depth test is enabled, no, there's an error here, but it's not that this should be and. So, not enabled. Does this make sense? So if GL depth test is not enabled, or pseudo depth is actually less than what's already in the z buffer, then we do what's in here. Does that make sense? So if GL depth test is not enabled, that means we're not depth testing. That means whatever comes in should just be overwritten right on top of what's there. We're not using a depth test. We're not checking depth. So this will give us true if GL depth test is not enabled, and then we'll go directly in here and do our thing. Make sense? If, however, GL depth test is enabled, then this gives us false. Then this needs to be true for us to go in here. So if it is enabled, we need to test the depth. If it's not enabled, it'll just go directly in. Does that make sense? Do you feel like this is the correct check now? You don't look convinced.
Isn't it equivalent to enabled and?
If we would say if GL depth test is enabled and this, then yes, we would go in here if it's enabled correctly, but if it's disabled, we do nothing.
Ah, okay.
So it does matter. This can be programmed in many ways, but kind of in one line, we're both saying we should do this if it's not enabled. If we're not using depth testing, we do this. But if it is enabled, then this also has to be true. All right, but this wasn't the main thing here. So we've added the depth test in here. Fine, so we've found these values, we find the pseudo depth. If we found that, we do what we talked about earlier. We're going to say, basically find v underscore x and set value to variable in Fragment Shader. So that makes sense. So our Fragment Shader now gets, for every varying variable we do this. Okay, so now we imagine that we have in our Fragment Shader correct values for all these variables. Yes? What do we do next? If we've set all the values for the Fragment Shader, that is, all the varying variables, all the values are set here. All the uniform variables values have been set just somewhere in our code before this happens. So the uniform variables should have the values we want them to have. The varying variables should now have the values they should be assigned based on whatever came in from P1, 2, and 3. So what do we do next? Run the Fragment Shader? Run the main function on the Fragment Shader? Cool, okay, so we run our Fragment Shader main function. All right, so this is, we've already looked at this. We've already kind of, this is a recap on this idea, just to kind of get us into where we want to be. So now, at this point, what we've hitherto done is to say, now we say our frame buffer, which is basically our color buffer that we want our colors to be in, number xy equals gl frag color, because our Fragment Shader main, like the main thing that that function should do is to set some value to gl frag color, right? We can do it in a lot of ways. We can program a lot of complex code there, but in the end, the only requirement for our Fragment Shader, so that it actually does anything that matters, is that it sets some value to gl frag color. And until now, we've simply taken that value and we've put it in the frame buffer for this pixel. So in the end, we have P1, P2, and P3, and we're basically filling them in with whatever color it should be, and we're just putting that right there. We've added the depth test, so that if there was something previously here that was actually closer, then that should still be there. However, if there was something previously here that was further away, then we should overwrite that. So the depth test will make sure that that stuff works. Now, you've all seen computer games where you have these semi-transparent things. You can see things through other things, and it looks cool. You've seen particle effects like explosions. And when you draw an explosion, you're really drawing a bunch of polygons, but they don't look like polygons, do they? No, they don't look like actual kind of piles of triangles or squares with images on them, even though that's what's actually being drawn. Instead, we only see the images. And if we have a fire or an explosion or something, we can see one part of it that overlaps another one, and you don't see it as if it's drawn on top of it, over it. Instead, you see them kind of meld, you see them blend. The more particles you have in this explosion, the more density there is of particles in the center of an explosion, they'll kind of add each other up and you'll get a stronger color, right? So this is an effect that we want to be able to replicate. So instead of it looking something like this, everything drawn on top of the other things, instead we want to kind of see the general effect here, and we want it to be strongest in the center and then kind of fade out from the sides. So that's a complex thing to do, an actual particle effect that does this. But the first thing to do is to make sure that every particle that we draw, or every polygon that we draw, is in some way blended into whatever it's drawn on top of. So if we imagine that we just have one objective with blending, and that is to make 50-50 semi-transparent things. I'm just going to make a simplistic blending here and say I want things that I put into the frame buffer to somehow look like they're 50-50 transparent. That 50% of the color that you see is the object's color, 50% of it is whatever you're seeing through it. Could I somehow do that here? Could I somehow change this line to accommodate that? Okay, so the frame buffer equals geofrag color times 0.5, okay. That's one part of it. But now we've just basically taken this color and we've made it 50% darker, and then we've just overwritten with it. Plus whatever is in the frame buffer already. Frame buffer number xy. So this is a value that we can both, or we, that are hardware implemented OpenGL, because this is not something we're implementing in the Fragment Shader, in the Vertex Shader, where we have the power to implement things ourselves. This is something that's just in OpenGL. Either way, this is a value that it can both read, both access and edit. So we access this value to get whatever's in here already, times 0.5. Okay, so we're taking this and saying this times 0.5 plus what we're sending in times 0.5 is what we end up with in the frame buffer. So is there anything that a programmer that uses this now needs to think about to make sure that, let's say there's just one object here that we're drawing in this way. What we want to do is there's some complex thing behind here, there's a house, there's a city, but we're looking at it through a window that's much closer. We want the window pane to be 50-50 some color, but 50-50 the stuff that we see through it. Is there anything I need to make sure to do properly? Let's to begin with say, if GL blending is enabled. Okay, if GL blending is enabled, we do this. Else, we don't do this. We just do what we did earlier. Frame buffer number xy equals GL frag color. Okay. My point here is this building here, it's not see-through. We want to have blending disabled when we do that, right? We want to have it enabled here. So my question now is, with this system here, making this solid building in the background and then having it 50-50 see-through, seen through this window here, is there anything I have to think about? The order in which I do things, what I switch on and off when I draw each object.
Should you draw all the solid edges first and then edges with the alphabet?
Okay, so draw all the solid objects first and then the transparent objects. Does that make sense? Because if I were to draw this window first, there would be nothing behind it to blend with. You can see that my blending is counting on the fact that the frame buffer already has what I want to blend with it. Because OpenGL isn't storing the objects that we send through, all the polygons that we send through. We can't go into a list of polygons that's there and see which one should I blend with and which one shouldn't I. I'm trusting that these have already been drawn. Anything that should be seen through this window is already drawn. Because what we also do here is, so if we have the depth test, can see if depth test here, test is enabled. What do we have to do that we haven't done yet if the depth test is enabled? We've done the depth test itself, checking if the pseudo depth is lower or higher. What's the other thing we need to do if depth test is enabled? We have to make sure that the Z buffer is up to date, right? So we also have to say Z buffer number xy equals our pseudo depth. Which means that if we were to draw this first, then not only will it not get anything to 50-50 blend with, because there'll just be a blank background here when the window is drawn. When we finally get to the point where the buildings are drawn, then this has already been put in front, so they'll not even be drawn because they'll fail their depth test. Make sense? We could then say, okay, how about I take all the transparent objects and I have depth test disabled? Well, in that case, it won't be 50-50, it'll just be right on top. So if we draw the window pane first, then either the building will be completely disappeared because of the depth test, or it'll just be completely flat on top. So the only way for us to make sure that it's 50-50 see-through is to draw the see-through object afterwards. So the things we need to make sure is GL blending is disabled when we draw the solid object, and the solid objects are drawn first, and then that GL blending is enabled when we draw the transparent object, and the transparent object is drawn afterwards. Questions regarding this? Does this seem like the extent of what you want to be able to do with OpenGL? A 50-50 transparency blend? Or is there something more interesting that you'd like to do? Like, what's the first thing that comes to mind that we'd like to edit here? Let's just little by little make this more interesting. Sorry? Some opacity. Right now we have 50% opacity. Basically we have 50% opacity or 50% transparency. It depends on how you look at it. So our opacity value here at this point is hard-coded 0.5. What would we like to put in there instead? Okay, so the alpha value of our fragment color. Now let's go to the other side of the board just a little. So we have a fragment shader here, and we set GL frag color to something that we calculate here in our main function, right? Now GL frag color, like any other color, has red, green, and blue values, and then it has the fourth value, which is the alpha value, which we're finally going to start using now. Up until now, when we've been using basically 4 components for our colors, we've always just put 1 in the last color, which is good because even if we would enable blending, we wouldn't see any difference if the alpha value is 1, not with regular transparency blending. What we want to do here, however, is we now want to say we can do GL frag color dot A, because GL frag color we can put each component separately in there as well. So let's imagine that somewhere here we have a uniform something variable, or maybe a varying variable, or I don't know. That is called, you can say, opacity. So U underscore opacity here. This is very explicit to actually have a uniform variable that tells us the opacity. Usually, instead, you'd say it's the 4th component of every color that comes in. So if I set a color to this, I'm going to have to take the alpha value. However, it can be confusing if you're going to apply your lighting calculations to the alpha value as well. So what we usually do is we say I'm going to choose one of the components here. So either I have uniform U underscore capacity, and it just says GL frag color equals U underscore opacity. That's just an explicitly set uniform variable. Or I can say I have some uniform variable here that's u underscore material diffuse color. And I'm going to say the fourth component in my diffuse color, that's the controlling opacity, right? That's the controlling alpha value. So I'm going to say GL color alpha equals u underscore material diffuse dot A. Okay, that's another way to do this. Another way to do this is to read, sometimes the material diffuse actually comes from somewhere here. We say we have some material diffuse that comes out of some texture with some sampler and some u underscore uv dot x and u underscore uv dot y. Okay, so our diffuse is coming from a texture. In some cases, if that is a 32-bit texture, then we can say that texture also includes an alpha value, so we can use that. Another thing we can do is we can say material diffuse comes from one texture, but then I'm going to say u underscore opacity, no, not u underscore opacity, just some opacity. So I could say opacity now equals material diffuse dot A, and then here I'm just going to say this equals opacity. It's often nice to do this, to grab this before we start applying lighting calculations and stuff to it. Either way. Or I could also say the opacity comes from another specific alpha texture. So I have some sampler alpha here with the same u underscore uvx, u underscore uvy. So I'm using the same UV coordinates, I'm using the same texture coordinates to sample into this image, but I'm sampling it into a different image. Does that make sense? So my alpha value, or we can do this, if it's a red, green, blue image that's simply grayscale, just go ahead and take one of the values from that, like red, and say the opacity, I have a specific grayscale image that is just telling me the opacity of things. And you can find these all over the internet. You can find for instance, if you search for leaf textures, you can find leaf textures where you have an image of a leaf with colors and stuff. And then you can find the alpha texture for that same thing, where you have the exact same image, except it's only the outline, and it's completely black outside, and it's completely white here. So basically, it's saying these are the colors for the leaf, but this is the alpha texture that you can use to make sure that you don't draw anything, you don't draw a full kind of box here as your leaf when you're drawing it in your program. Instead, you're only drawing the leaf. Because you set 0 alpha for everything that's outside the actual leaf in the image, and full alpha or full opacity for whatever's in the leaf. So if you take your opacity from a texture, if you're rendering this part of the polygon, it's just going to become see-through. Stuff like this. You can even add into your shader something that's called like an alpha test, and actually say if the alpha is 0 or something that's so close to 0 that you decide that it doesn't have any effect, then you can simply call discard. You can do something like if opacity, you can say equals 0, but usually you'd say something like is less than some threshold value here, something very small. And you can simply call discard, and the fragment shader will stop and it'll throw away whatever's happening, and it won't continue. Won't continue into the blending, won't continue into everything. So things like this, you can have an alpha test to check that the alpha value that you're using, however, if things should be semi-transparent or around the edges that you want it to kind of feather, then we have to go into the actual blending. So I'm going to go back to here and say now we have something on the GL frag color that is an actual alpha value. So now I can change this and say my opacity, so GL frag color, times, instead of 0.5, I'm going to say times GL frag color dot A. So the red, green, and blue values of GL frag color will all be multiplied with the alpha value of GL frag color, all right? Plus what's already in the frame buffer at XY, but times what?
Opacity.
The opacity here is the alpha. Do we also do this times the opacity?
1 minus the opacity of the value in the frame buffer.
Is it the opacity? Should the opacity or the alpha value of whatever's in the frame buffer affect how we see through the window that we're drawing now? Not really. So if we're just thinking about simple transparency, the only thing the alpha value adds here is we can decide how transparent something is. Is it 20% transparent? Is it 80% transparent? So somebody already said 1 minus, right?
Yep.
So 1 minus GL frag color dot alpha. Okay, so we're basically saying whatever we send into the frame buffer now is a weighted average of our fragment that we have now and the fragment color that's already here. So we have a fragment color that's already here. We have a fragment color that we're sending in. We take a weighted average of the two. What decides this weighted average is the alpha value of what we're putting in. So if that is 0.8, 80%, then we'll get 0.8 times this, 0.2 times this. If this is 0.5, we're going to get the 50-50. If this is 99%, we're going to get 1% of this. Okay, so this makes sense for transparency. So now we've fixed our idea with the hard-coded opacity. Now we have an actual opacity value. Make sure, should we take a break or something before we continue? Would you like that? Some coffee? Let's take around 5. But while you're drinking your coffee, you can think about what else do we want to add here? You know, we fixed the whole hard-coded opacity thing. Isn't there something more we'd like to do here? Shouldn't this be a little bit more flexible than only this? So, who's been wondering about how we could make this more powerful? There's some insane amount of light coming from somewhere. Right here. No, not this. I'm going to see if I can lower the blinds even more and make the light here a little bit more even. All right. So I want to kind of take this line out here. We're just saying, okay, we have the geofrag color, multiplying it with its alpha. We have what's already there. We're multiplying it with 1 minus geofrag color alpha. Not that this isn't a blending policy that is very common and very good. This is just regular transparency. And it's probably one of the most used policies for blending in OpenGL. You'd probably put your money on it being the most used, but I'm still not sure. Because if we go into the idea of a particle effect, for instance, would something like that work to create an energy effect? If you want something like fire that's somehow kind of moving, you can't really make a single model doing that entire fire. That's a really complex animation just to get something like that. But you kind of want its center to be really bright. You want it to fade out. You still want this motion. It's something that you'd like to do is to say, okay, I'm just going to make a single, it's called a sprite, which is basically just a texture image projected onto a single polygon or a single quad, a single square. I'm just going to put this here, and then I'm going to put a bunch of these little squares, each one on top of each other. Except I'm going to use blending so that it's black here on the edges. So the black, either black or with no alpha value, will mean that it'll become completely transparent, or so you won't see these boxes here. But I'm going to have it fairly bright in the center, and then I'm going to have it fade out to this black here. But a single circle here isn't my fire effect. But if I put hundreds of those all over the place here, concentrate them most in the center, but then make them fade out. I know it's hard to see here when I'm pointing to a whiteboard, but we'll do this in a program as well and see cool effects. Even better if someone could actually do it themselves and come and show us next Monday. Either way. So we have this kind of bright center here fading out to somewhere else. And here we concentrate them, but we get fewer and fewer as we get to the edges. So we get this concentrated energy here, but it fades out to the edges here. But we have the motion because all of these are also kind of moving away from the center. We create them at the center where they're concentrated, and then they kind of move out of that center. Give us a fire energy effect. Explosion is a very simple thing to do because you always want it to just be 100% concentrated in the center first and then just fade out over time. So how can I get this concentration effect? Like, let's imagine just another policy for blending. Let's not make something that's so generic that it can do all of them. Let's just think about what would this policy be? If I draw a sprite here, and I've already drawn a lot of this effect, do I want this sprite to say I'm going to take my alpha value and multiply it with my color, and then I'm going to take the rest, 1 minus my alpha value, and multiply it with whatever's behind me? Is that what I want? Do I then get this concentrated energy that builds up and builds up and builds up as I add more? Not really, because I'm always diminishing it by 1 minus, by the rest. So in that case, I'd actually want to say I'm going to take the new sprite that I'm drawing, multiply it with my alpha value. So I'm going to say this is GL frag color times GL frag color dot alpha. So I want to take my opacity, my alpha value, and multiply that with the color that I'm adding. Because maybe I don't want this sprite to be so strong that it's overpowering. I just want it to be a little addition to the overall energy effect. So I'm using my alpha value. But I want to add this to whatever's in the frame buffer. Multiply it by what? It's not multiplied by anything? 1 multiplied by 1, okay. Yes, that's actually the effect that I want. But I don't really have to multiply it with 1, do I? I just need to not multiply it with anything. So in this case, I'm taking this, multiplied with its alpha, but I'm just adding it on top. I'm adding to the overall effect. I'm adding energy to it. So the more sprites I put in there, the brighter this will be. In the end, it'll just wash out. It'll become bigger than 1. That's okay, because OpenGL caps its colors on 1. If you go over 1, it simply caps it on 1. So that's fine. So in the end, you'll get this concentrated center that'll either be white, or if one of the color components is missing from the sprites, it'll just be a full strength of whatever color components are in that sprite. And then as you go closer to the edges where there are fewer sprites, the buildup will be less. Does this make sense? So now I've said I'm sometimes multiplying this with 1 minus the alpha value. Sometimes I'm multiplying it with 1. Maybe I want to skip the alpha value here and just multiply this with 1. Just say I want to simply take this value here and I want to add it on top of whatever's there. No alpha value, nothing, no diminishing, just stick it on top. If you do this, for instance, you can project an image kind of onto background. It looks like you actually turn on a projector and just project it on whatever three-dimensional thing is behind it. Have you ever seen a projector turned on when there isn't any projector screen behind? It just kind of projects onto whatever's behind. So you can take a texture image and you can simply put it somewhere in front of the camera after you draw everything else, and you can say, I'm just going to add that plus whatever's in the frame buffer, no alpha value on anything. I'm just going to take this pulley, add it on top of this, and it looks exactly as if you have a projector projecting onto a background. Make sense? Okay, so that's one thing you might want to do. And then there are a million other things that you might want to do, kind of mixes of this. Some of them I could name a real-world example where this, looks like that. In some cases, there is no real-world example, but still, it's computer graphics. You want to be able to do, sci-fi stuff as well, or just stuff that doesn't make sense, or just psychedelic weirdness, because that's what computers are for, to make stuff that isn't real, right? It's the main goal of computers. So how could I accommodate this? Like how can I make this work? Sorry? Well, yes, it's kind of more flags, true. So I'm simply going to say here, all right, I'm going to put something in here that I'm going to call the source factor. And I'm going to put in something here that I'm going to call the destination factor. So I'm multiplying this with some source factor, I'm multiplying this with some destination factor. Now I need values for these. So my source factor, just do something like get source factor here. This is not an actual function inside OpenGL, this is just me making a function so I can go to someplace else on the whiteboard and continue this. Get source factor here, and I'm going to make some destination factor. I'm going to say that equals get destination factor, and as you said, yes, we're going to use more OpenGL flags to decide what this source factor or destination factor will be. Then we use these factors here to multiply this, and that's our blending. So I'm wondering where exactly I should go to continue with this, where it's fairly easy to read off the... I'll just switch over to this board and erase some of this for now. Just set this up again later. Okay. So let's imagine we're now making these operations get source factor and get destination factor. So get source factor here, what that operation does is it checks an OpenGL flag. I don't know the name of kind of the variable within OpenGL, but I'll tell you how we set it. So the idea is we have some kind of, let's just call it source policy. Again, I'm not sure of the terminology here, but we're imagining we've set some policy for what the source factor should be. And let's say if the source policy is GL source alpha, then we're going to say return, we can even do get source factor xy, something like that, and say, okay, this is, we're going to be using the frame buffer, return whatever's in the frame buffer at xy. So let's just stick that in there as well and say we're going to get the source factor for this particular pixel, xy, xy here. All right, so we're going to return frame buffer xy dot a, and this should be like this to keep consistency. All right, else if the source policy equals GL1, return 1. This is an actual flag in OpenGL. We can go ahead, it can be GL0, it can be GL destination alpha, it can be GL source color, GL destination color. We'll go through some of these flags later. Same with get destination factor. Then we can imagine that we have some destination policy. So if the destination policy equals GL1 minus source alpha, then we return 1 minus whatever's in the frame buffer here at xy dot a. Else if the destination policy equals GL1. So all of these different flags could be used as the blending policy for both the source and the destination. So I can, for instance, set both the source and the destination to GL source alpha. Then the actual alpha value of what we're putting in there will be multiplied with both of them. So again, return 1, and then on and on and on. Now I'm going to go back to here. So what we're looking at is that somewhere in our code we say GL enable, GL blending, like so. Okay, so we've enabled blending, and that obviously, has an effect on our rasterization, or whatever happens after we've run the fragment shader. Then we're checking if blending is enabled, and then we do the blending. So one thing we need to do is call GL enable GL blending, and we can also call GL disable GL blending. Like for anything else we can enable, we can also disable it. Then we call GL blend, it should be lowercase here, GL uppercase B, blend uppercase F, func, or function. And I don't understand why they didn't just have it blend function. They're not saving that many letters. GL blend func. Here we can send in something like GL source alpha and 1 underscore minus GL, no, sorry, it's GL1 minus source alpha. How did I write it? Yeah. Source alpha. So in this case, what I've set up exactly here is I've set up OpenGL for the regular transparency blending that we looked at first. I'm just saying I want the source fragment, which is the fragment that we're sending in, to be multiplied with its alpha, with the source alpha. I want the destination fragment, which is whatever's already in the frame buffer, to be taken, multiplied with 1 minus source alpha, and then I want to add the two together, and then I want to put that in the frame buffer. Yes? So I can also move this around and take whatever was already there and multiply it with the alpha value, and the other with 1 minus source alpha. It'll be super weird because it doesn't make any sense that the opacity of an object that I'm drawing now affects the stuff that's in behind. It should affect, this, but I can do it. So I can use, in this case, we have GL source alpha. We have GL destination alpha. So I can take the alpha value of what's already there, destination alpha. I have GL source color and GL destination color. Who can guess what those do? So source alpha, it takes my red value and it multiplies it with the alpha value of the source. It takes the green value, multiplies with the alpha value of the source. It takes the blue value, multiplies with the alpha value of the source. GL source color and GL destination color, they take the red value of whatever color it is that I'm using at this point, and then they take the red value of the source color and multiply it with red. And they take the green value of whatever I'm using now, and take the green value of the source color and multiply that. So they just take the components and multiply them together. So rather than using the alpha value, we use red for red, green for green, blue for blue. However, if we use GL source alpha or destination alpha, we use the alpha value. We have GL1 underscore minus underscore all of these. GL 1 minus source alpha, 1 minus destination alpha, 1 minus source color, 1 minus destination color, 1 minus source alpha, etc. We have GL1, we have GL0. I don't remember anymore right now. So okay, these are all our different policies. So we're basically saying we can put each of these policies into the source policy and into the destination policy. Does that make sense? So these are just OpenGL switches. Source, the one that's first. Source is the fragment that we're drawing, whatever's coming out of the current run of the fragment shader. The destination is whatever's there in the destination. We take the source, we take the destination, we multiply them with a factor, but this factor is decided based on the policy that we send in to GL blend func. So this is a bit complex, but this is kind of the entire thing. If you go online and ask for how to do transparency, you'll always get just this one answer. It'll say, okay, enable GL blending, do GL blend func, source alpha 1 minus source alpha. But there's no explanation of what does that mean. You just stick it in there and suddenly it works. And you can change your alpha value and the alpha value has an effect. It's pretty powerful to actually understand what this does. The first thing you set in here is not a specific number. It's a policy for how to choose the number that will be multiplied with the fragment that you're making now. The second number, again, it's a policy for how to select the number that will be multiplied with whatever's already in the frame buffer in the same pixel that you're rendering into now. You take the two, multiply each with their factor based on the policy, you add the two up, and that's what you stick into the frame buffer at that point. Does blending make sense? Does it make sense that this would work and this would do what you want it to do? Okay, so I'm not going to write here in full all of the code behind this, but the idea is we find the source factor, we find the destination factor based on these policies. These policies are set using GeoBlendFunc. So in your code, it's super simple. Just call GeoEnable GeoBlending, GeoBlendFunc with some two OpenGL flags, and boom, blending is happening. And then yeah, our frag color basically is our source color. Frame buffer number XY is our destination color. So this is source, this is destination. And that's what we put into the frame buffer if we're enabling blending. Yes?
Where do you call these functions?
These functions. Yeah. These functions are simply somewhere in your Python code.
Something that we will set there.
Yeah. And you can call, for instance, GeoEnable GeoBlendFunc in some specific policy for one object. Then before you draw the next object, you call GeoDisable GeoBlendFunc, because that's not supposed to be see-through. Then you're going to do some energy effect or fire or explosion. And then for all the sprites you call GeoEnable GeoBlending and some other policy here, something that is a policy that makes an energy effect. So this is just you setting values for variables in the OpenGL state machine. And once you set something here, it's going to be like that in OpenGL until you set something else. So if you enable GeoBlending, blending is enabled until you tell it not to be enabled. So yes, this here is just code that's in our case, Python code, or just in your main program code that's using OpenGL. This code here, however, that I'm writing, this pseudocode here, is kind of, we're imagining this is inside OpenGL, inside the rasterization algorithm, and we have no bearing on this. This is not code that we need to replicate or write. This is something that happens. That's why I'm allowing myself very much pseudocode and not too exact on exactly in which order this happens. What we need to know is depth test check first, because if the depth test fails, none of this will happen. Then we run the fragment shader. So we run the actual fragment shader here, because then we have values for a fragment. Then blending happens. So blending is not something we do in the fragment shader. But we can have a huge effect inside our fragment shader on what happens in the blending. We can even do things like take some distances or something and make those affect what the alpha value will be that OpenGL will then use for its blending. We can do all kinds of things. So if we have a fragment shader here, fragment shader, let me just draw Vertex Shader here as well. Vertex Shader. So in the fragment shader, at some point, we end up saying GL frag color dot alpha equals something, and whatever we set into the GL frag color here, into the alpha value of the GL frag color, at some point we set the color for it. Remember, I'm just adding this. We set GL frag color dot A equals something. That will be our alpha value, and that will affect how the blending works. Because usually we're working with the alpha value. Using source color or destination color as a policy is something that there's no, or not in my knowledge, any real world effect that would help you replicate. But it can be really cool to do things with that. You can get a very interesting kind of projector effect where you actually kind of emphasize certain colors and things like that. But you can play around with that, but usually we're using the alpha value. Either we're just using GL1 or we're using the alpha value. That's the most common. But we can use alpha values in different ways. And setting the alpha value for GL frag color, which we do in the fragment shader, will affect the blending. And we can do all kinds of calculations here that affect that. We can take it from a texture. We can take it directly from the diffuse color or from an explicit opacity uniform variable. But we can also take it from calculations. We can do some distances and have things fade out into certain directions and use that as our alpha value. We can do super cool effects in our shader. Are there questions regarding this idea? Because this is something that's just super fun to experiment with. So I hope everyone is thinking about, oh, I'm looking so much forward to getting back to my laptop to experiment with this, rather than, oh, I'm looking so much forward to getting home, to bed, sleep through the entire weekend. Anyway, that's me. Does anyone here feel like there's something we haven't covered regarding blending? I think blending is pretty much covered here. We'll look at more stuff when we have a programming session and actually look at it on the projector. One thing I want to look at a little bit, you have done though an example from it. You did fog in your shader programming example on the hand-in assignments, but I kind of wanted to look at that a little bit as well. And you probably have a fresh view on that, having done it recently, so we can get the answer from there. So in order to implement fog, which is a very common thing to implement, and in the static pipeline OpenGL, fog was just one of the things that happened in here. Fog would actually be based on values that we were working with here. Rasterization would include fog as well, because we didn't have the programmable fragment shader or vertex shaders. Instead, OpenGL just implemented things like distance attenuation and different types of attenuation on lights. It implemented things like fog. And so this was just implemented here. However, now in modern OpenGL, for better or for worse, if we want those things, we need to implement them ourselves. So more modern versions of software aren't always easier to use, even though that's kind of a trend. And in graphics, it seems like the more modern graphics libraries get, the more you have to understand to actually do all the stuff that you have the power to do. So, did the fog happen in the fragment shader or vertex shader? Fragment only? Or were there things you needed to do in the vertex shader to support it?
I calculated distance in the vertex shader as a varying.
Okay, so we have the distance in the vertex shader. Let's say we have something, 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 then we have position equals the model matrix times the position equals view matrix dot position, and finally we can just say GL underscore position equals the projection matrix times position. Okay, so we have lines like this. Where did you calculate your distance?
After the view matrix.
After the view matrix, so in I coordinates.
Yeah.
And what was the, did everyone do that? Or did, by a raise of hand, who calculated their distance that they used for the fog in global coordinates? Who did it in I coordinates? Both?
I mean, just different iterations.
Okay. Okay, so you tried both? So if we do it in global coordinates, what will that distance be? I imagine we have some v underscore, you can call it fog distance or whatever. Basically the distance to the vertex that we're drawing. So what would it be here if you calculate this in global coordinates? At some point we have the vector v, right? We already have the vector v, which equals the camera position minus our I position. No, that's the same thing, sorry. Let's say I position minus our position, just, our vertex position, right? Okay. And our fog distance, would that just be equals what? The length of v. Would that work? Okay. So here I'm calculating an actual length of v. If I calculate this in I coordinates, how would I do it there?
It's the
Because you know you're locating 0, 0, 0, then it's the length to the position.
Okay, so I'm located in 0, 0, 0. So then we can basically take position in I-coordinates and just say that is a distance to a vector, or that is basically the coordinates of a vector. So we draw it something like this. Basically here, our I is in the center, the point is here, then I can just take a vector with the exact same coordinates and take the length of that vector instead. Okay, so what I save is the minus here, the difference, but I don't save the length. Can I somehow also save the length? Is there a value here that I can just use? All right, so can I take this here, which is basically minus z in I-coordinates, and just use that? Yes, no? Will it give me the same effect? No, it won't be exactly the same. However, I'm going to try this. Position, or sorry, minus position dot z. So it won't give me the same effect, because what I had earlier is my fog will close in at an equal distance. So it'll be equal thick, the fog, at this length, at this why did I forget the word for fjarlægð here?
Length.
Not quite length.
Distance.
Distance. Thank you. So at this distance, we'll have the same kind of value for our fog. If we use the z value instead, we have the same value for the fog, the same thickness of the fog for this line. And as this line comes in closer, the fog will get thicker further away, thinner as we go in. And this is actually the way the static pipeline did this. It just used minus z for the fog distance, and it was okay with the fog not kind of closing in at an equal distance, but instead at an equal z value ahead. So it kind of closed in like a wall rather than closing in like a circle. I'm not saying one is better than the other. This one is a little bit better optimized. This one probably looks a little bit cooler. But you should definitely try both. And if you feel in your particular program that it doesn't make a difference on how cool it is, then this one is a little bit cheaper. But if it really makes a difference and you're like, it just doesn't make sense that the fog closes in like a wall rather than closing in like a circle, go ahead and use the length. Anyway, so this is kind of what I see as the difference between doing it in global coordinates and doing it in I-coordinates. Is in I-coordinates you can just go ahead and use this z here. The same as with the static pipeline and specular calculations. I'll take that question, or is there something?
I was just going to ask about the optimization of squaring the length.
Okay, yeah, I see. So instead of actually taking the length, taking the square root, instead just taking the dot product and using the length squared. Yeah, then you just have to be consistent with what value you're comparing to. Then you're comparing to a squared value. And then, yeah, that's definitely good as well. As long as it works. I'm wondering if the fog will not be completely linear then?
It's not going to be linear.
Not going to be linear, but if it looks cool, then it's good.
Maybe exponential.
Yeah. But in the end, it's kind of something fading into a color in the distance, and so maybe exponential just looks cool, or logarithmic or whatever. However, I was going to say, in the static pipeline, with specular calculations, OpenGL would also just, when it was doing specularity, it would calculate the lights in I-coordinates so that it can just use the vector 0, 1, 0 as the vector v every single time. That's another thing that the OpenGL static pipeline did. It just said, this is a vector that's pointing towards the camera always. And it kind of works. If you're here, it's actually pointing here, but the true vector should be pointing here. So OpenGL allowed you to set a flag that was called local coordinates. And if you set this local coordinates flag true, it would actually calculate the correct vector here. But if you didn't, and by default, it would just use this straight back vector. It's a little bit cheaper to calculate, a little bit less exact. Anyway, those are these ideas. Let's go back to the fragment shader for the fog. what do you do next? So what variables do you need here for the fog? Okay, so we have some diffuse color. Well, let's just add the variables that we actually need to add for the fog. Otherwise, I'll fill the entire whiteboard with.
Start and end.
Okay, so we need some kind of fog start, which is a distance, and fog end, which is a distance as well. Is that enough? I guess. We have the fog distance here. Well, we need the v underscore. So these are uniform variables. We need a v underscore fog distance here, and our rasterization will make sure that we get the correct linearly interpolated values for that here. So in our main function, well, we need a fog color though, right? So we need a fog color, which is whatever we're blending into in the distance. Usually that'll be the same as our clear color that we set in our program as well. Okay, so in main, we do some stuff. In the end, we can actually just do it afterwards and say, okay, we have GL frag color here equals something. Obviously, we'd probably make some color here, equal that, and do it with the color and set the frag color later. Let's just call it, yeah, final color. Final color before we added the fog. So if we add the fog, what do we do here then? The final color is something. Now we want to add the fog to it. So how does that, isn't that pretty similar to what we're doing in the blending? We're taking our fog color and multiplying it with some factor, and we're taking our final color and multiplying that with some factor, and then we're adding the two together, and that's the color we're going to use. So it's more or less the same thing as blending. So what are the factors? I'm going to say u underscore fog color times something plus my final color times something, and I'm going to say then GL underscore frag color equals this. GL frag color equals my fog color times something plus my final color here that I've calculated from the lighting calculations times something. So what are these factors going to be?
They show where the object is located within the start and end distance.
Okay, so I have some fog distance here, which is the actual distance. So let's just make this ratio here. My ratio equals, and that's v underscore fog distance, what, minus fog start, v underscore fog start.
That is over and minus start.
Okay, this entire thing divided by u underscore fog end minus u underscore fog start. So end minus start is the whole, fog distance minus start is the part. So this is part divided by the whole, which gives us the ratio. So this is our ratio. Fog color will be multiplied with the ratio. Ratio, we can call it fog ratio if you want. Fog ratio. Fog ratio. And this will be multiplied by 1 minus the fog ratio. So does this make sense? So adding this here, we get fog. And there are a lot of things we can do with fog. One of them is we can use fog to be able to far plane clip closer. So we can actually have the fog so that it fades into the far plane. So our fog end and our far value in our projection matrix setup are the same value. So that means we don't see far plane clipping. Instead, we kind of fade into the far plane clipping. We set fog color to the same as clear color. We set fog end to the same as the far plane. And then we're simply allowing ourselves to fade into far plane clipping so we can clip closer, which means we can throw away more stuff that we don't need to render and render smaller areas. And originally that was what fog was mostly used for. It was just to be able to just to be able to render the three-dimensional games that we wanted to play, because it was just so expensive to have everything inside. If you look at modern games though, if you go into Zelda Breath of the Wild, you just stand there and you look way into the horizon and everything's there. There's nothing obscured in fog, everything's just there. So obviously fog is not as important just as an optimization anymore, but it can be a cool effect as well. And originally it was something that was just part of the OpenGL pipeline, part of the static pipeline was being able to do fog, because it could be so important just to be able to optimize by far plane clipping closer. Yeah. Are there any questions regarding this? Blending, fog, which is a type of blending, but a blending that we have to do in our own shader.
Do you think it's any different? I did the ratio calculation in the Vertex Shader and just like had a v underscore fog factor that I sent. Like
I don't know.
0.01.
Right now, just looking at it, so the question is, if we just have a v underscore fog factor and we actually do the ratio calculation here, we do fog distance, we have fog start and fog end as uniform variables in the Vertex Shader, do this entire thing. If we look at a polygon here, so this is maybe closer to the camera, so this will get a higher fog factor, then it'll linearly, no, actually that makes sense. That's probably a great way to do it. So yeah, we could do the ratio. However, again, like with the difference between doing it here and just using z, doing it here with the actual distance, try all three, see if you can see a difference. If you can see a difference, but the difference isn't enough to trouble you, go ahead and do it, because it seems cheaper to be able to do a whole calculation in the Fragment Shader rather than the Vertex Shader. So yeah, I'm not going to say yes or no to that at this point.
Which way around? You were pointing at Fragment Shader and saying Vertex and vice versa.
Okay, so again, taking something out of the Fragment Shader and doing it in the Vertex Shader is an optimization. It's cheaper. So if we can do that, we're making everything run faster. Just like originally, the whole lighting calculation would be done in the equivalent of the Vertex Shader. In the static pipeline, we didn't have the shaders, but the equivalent of the Vertex Shader happening in I-coordinates, the lighting calculations would happen here, and they would simply linearly interpolate the color over the polygon. But then we couldn't actually get specular effects and stuff within a polygon. Only if it had landed on a vertex, it would be interpolated over the vertices. So now we like to do lighting calculations in the Fragment Shader. It's more expensive, but it looks so much better that it's worth it. But if you can do something like this, like the fog, and just take a calculation and do it in the Vertex Shader instead, and you actually don't see the difference, then it's definitely a better place for it to be. It's just, I'd say, yeah, 100% true. If you can do something in the Vertex Shader and it doesn't affect how cool something looks, the Vertex Shader is a better place for it to be. Because then you only have to linearly interpolate it before you set it to whatever variable you want to use it here. Whereas if you calculate things in a Fragment Shader, they're being calculated for every pixel rather than for every vertex. So that's just the thing. The Fragment Shader is run hundreds of times more often than the Vertex Shader in most programs, especially in high resolutions. Then each vertex has a lot of pixels inside them. So the Vertex Shader 3 times versus the Fragment Shader for every pixel that a triangle affects. Depends on the system how much more often it is, but yes. That was the long answer for a short question. It's okay if it looks right. Did you just do it like on the paper, or did you actually try it?
Yeah, I tried.
Tried it in a program as well?
Yeah.
And it looked like nice fog?
Yeah.
Then cool. Other questions or ideas regarding this? Okay, so next Monday session, obviously we have the assignment, so a lot of people will be working on that. I'm also going to look at some blending, maybe fog, particle effects, things like that, just program interesting stuff on the projector, see cool things happen, hopefully kind of throw ideas around and make interesting graphics. But then we're actually kind of running out running out of class time this semester. So I think this is the last kind of lecture where I'm adding information. Next programming session will be working on transparency, blending, things like that, and your next assignment. After that, there's a lecture which will mainly be an overview lecture, GL pipeline overview, maybe do some practice examples and things like that on the whiteboard, but no new material. And after that is just the last programming session where we'll kind of have a little bit of a semester harvest and kind of look at cool things we've been doing and stuff like that. So anyway, have a nice weekend.